this year. We'll talk about complexity of the isomorphism problem for subshifts.
Thank you for the invitation and for covering all my travel expenses. So I'm going to talk about the complexity of the isomorphism problem for subshifts. So this is sort of on the interface between descriptive set theory, which tends to measure somehow complexity of various sets and functions and so forth, and some dynamical systems in which I'm not an expert, so it's very easy to ask me a question that I probably won't be able to answer about the dynamical systems part. The descriptive set theory part I pretty much know. So should probably start by telling you what we're looking at. So what is a subshift? We start with a finite, think of this as an alphabet, some finite set of symbols, maybe 0 and 1, A and B, what have you. We could have more. We look at all of the bi-infinite sequences we can form. So go in both directions, not just from one side. There is a one-sided shift too, but here we'll be looking at what's called a two-sided shift. By one-dimensional, we just mean that it just runs, let's say, left and right. We have higher dimensional subshifts that can shift up and down and left and right as well and so forth, but here we'll just start by looking at one-dimensional. So we look at all of these sequences and we look at them with the shift map or the left shift map. And the idea is we just think of the sequence as indexed by the integers. Well, the shift of a sequence, we just move everything over one position. By a subshift, we mean, well, take some subset of this, some collection of sequences, but we still want the shift map to be well defined. So we want this to be what we call shift invariant. If a sequence is in there, we want its shift in both directions to be there as well. And we also want to have a nice topological space. So there's a natural topology on the space A to the Z, where we just give A the discrete topology, finite set, and we look at the product topology. This is a zero-dimensional space. It's homeomorphic to the Cantor set. And so we want to look at a collection of subshift as something that's both invariant under the shift and also topologically close. It gives us a nice metric space, or well, topological space here. We won't worry about the metric. We say that two of these are isomorphic if there's a map between the underlying spaces. It's both a topological morphism, it's a homeomorphism, but it also commutes with the shift. So we have the picture, I'm calling them X and Y. So I have X and Y, the shift map in both cases. And here it's just saying that I have, forgetting what I called my map, B. It's just saying that this diagram commutes. And so this is what we want to think of two of these as being the same in this case. And there's a basic result. It's actually somewhat simple in the sense of what these possible isomorphisms can look at. It's actually a very easy theorem to prove using the shift invariance. It's like a three-line proof. But it says that an isomorphism, in fact, any morphism, just something that commutes with the shift map, is always given by what's called a block code. And saying we have these bi-infinite sequences, and if I want to figure out where one of the sequences maps to, and I want to figure out a particular digit, there's just some fixed window you have to look at. Just look at those symbols in that fixed window to figure out what digit that gets mapped to. This is called a block code. They can have different size windows, but it's always finite. So each particular block code is always, we're just looking at sequences of some finite length and mapping them to one of our symbols in A. So they're only a finite number. For a particular block code, there are only a finite number of different things that can change. Here's a quick example of this. Suppose I take X to consist of all subshifts that have a 0 followed by either let's say 2 or 3 1s and then a 0 and then 2 or 3 1s. These are the only patterns that I allow. This is a subshift because, well, I allow these to shift in both directions, and it's actually check this closed. And let's say I take Y to be the sequences that always have 2 zeros together and either 1 or 2 sorry, one or two ones together. Well, I can see that these two subshifts are actually isomorphic because I can take a block code that looks and says, well, if I see, I can actually ignore things. It says if I see a 0 at the space I'm scanning, we'll put a 0 in. If I see a 1 with a 0, and it should indicate this is sort of the center of where I'm scanning. If I see a 1 with a 0 immediately to the left of it, I'm going to put in a 0. And if I see a 1 with a 1 to the left of it, I would put in a 1. So just scanning here, I have a 0, I would copy in a 0 here. I have a 1 with a 0 to the left, I would put in a 0. Here I have a 1 with a 1 to the left, I would put in a 1. Now, if I line this up correctly, this 0 gives me a 0, this 1, because of the 0, gives me a 0. This 1 gives me a 1, and this 1 gives me a 1, and so forth. In fact, this is 1 to 1 non-2, so this actually would be an isomorphism of these two subshifts. But again, I only needed to look at one symbol and one symbol to the left. And here, the block code would actually be saying that I'm sending, fully explained, would be saying I'm sending 0, 0 to 0, 0, 1 to 0, and those would be the 4 possible of these finite windows that I would need to describe. So these are nice. Isomorphisms between subshifts have this particularly nice structure. In particular, this tells me that there are only countably many different functions because each block code has some finite window. There are only finitely many block codes with that particular window, so there are only countably many block codes that I need to consider. Not all of them give isomorphisms, not all of them are one-to-one, but at least all of the isomorphisms are among that countable set. And in fact, these are all, maybe the only one who's interested in this particular fact, but these are all computable maps. They're very, very simple maps. There's another common way of thinking about a subshift. We can define it as, well, here in this example, I sort of described what the possible patterns were. The more common way is to describe what patterns are forbidden. So we often describe a subshift by saying it's all possible bind infinite sequences that don't contain the following patterns. So I might say I don't want to include 2 zeros in a row, or I don't want to include the pattern 1, 0, 1, 0, 1, something like this. Is called a set of forbidden words. And for any set of forbidden words, we can form the sequences that don't include those. Now, 2 different sets of forbidden words might give me the same subshift. For instance, if I say eliminate the pattern 1, 1, 0 and the pattern 1, 1, 1, this would be the same as saying, well, just eliminate the pattern 1, 1. Don't allow that. So I can have a different collection of forbidden words, but there's always a maximal one that I could come up with. Take all of the words that don't appear anywhere in all the finite patterns that don't appear anywhere in my subshift. And we say a subshift is of finite type. This won't come up in this talk, but these are ones that are actually studied quite a bit. If we can find a finite collection of forbidden words that introduces the subshifts. These have a particularly nice structure. A lot has been seen about them. So I'd like to know, well, what can we say about classifying these up to isomorphism? How difficult is this problem? So this has been studied. There are a number of things that are invariants. For instance, we can look at the topological entropy of a subshift. There's a sort of nice way of calculating that. But how complicated is this? It turns out topological entropy is not a complete invariant. You can have non-isomorphic subshifts with the same entropy. So we might want to think about what sort of invariance, if we wanted to give complete invariance, some collection of descriptions of our subshift that completely describe its isomorphism type, how complicated would this have to be? Again, more is known about finite type, but we'll be looking, there are only countably many subshifts of finite type, and so really we want to look at all of them to see something interesting from the descriptive set theory standpoint. These are all things to say. And so we're going to look at this from the viewpoint of descriptive set theory. We're going to ask somehow how complicated is it to describe when two subshifts are isomorphic, or another way of saying this is how complicated would a complete system of invariants for isomorphism of subshifts have to be. So there's this whole program, which I'll come to in a minute, of what I mean by this. But the idea would be to roughly say, well, is this describing subshifts up to isomorphism? Is it more complicated than, say, describing groups up to isomorphism, or describing linear transformations up to isomorphism, or something like this? We can gauge different sorts of classification problems in terms of roughly how complicated would a system of complete invariants need to be for each of them. That's the first thing that we want to talk about. So, talk about a Borel equivalence relation. So, we start on a polar space. So, this is a separable, completely metrizable space, or just think of it as a complete metric space. They're essentially, all the uncountable ones are essentially, well, up to some Borel measurable map. They're all essentially the same as the reals, but it's more convenient often to work on other spaces. We can look at the equivalence relation as a subset of x squared. And so we can talk about how complicated it is. So the Borel sets are what we get by starting with the open or equivalently closed sets and closing under complements and countable unions. And we say an equivalence relation is a Borel equivalence relation just as a subset of x squared. It turns out to be a Borel set. And these sets have particularly nice structure. They're all the big measurable. They have the property bear, a lot of other nice what we call regularity properties. So they're somehow the simple, at least, I mean, they're not quite as nice as open sets, but they're reasonably well behaved. You don't end up with any sort of real topologies when you look at them. How do we compare two equivalence relations? Well, we have this notion of Borel reducibility. We say that if I have an equivalence relation E on a space X and another equivalence relation F on a space Y, say that E is reducible to F, Borel reducible, if we can find a function from the underlying space of E to the underlying space of F, so that two things are E equivalent precisely if their images are F equivalent. Now, the right way to think about this is giving us an injection between the two quotient spaces, which has a nice lifting back to the underlying set. So Borel, we can represent this injection of the quotient spaces by a Borel map on the underlying sets. But sort of the intuition behind this is saying that the quotient space of E is smaller, or at least no bigger, than the quotient space of F in a definable way. We can, in general for infinite sets, we say one is no bigger than the other if there's injection from one to the other. And it's the same idea here. We're just asking that the injection actually be suitably nicely definable. We don't have to use the axiom of choice, say, to find it. And so we have this notation. Also sometimes talk about an injective, what we call an embedding of E into F, where we take our function to be injected. But that doesn't, it's a little bit nicer, but in terms of the quotient spaces, it doesn't really tell us that much more. And I guess that's what we just said. In terms of classification problems, having Borel reducibility from one equivalence relation to another is somehow saying that the types of invariants we would need for E are really no worse than the types of invariants we would need for F. If you think about what sort of things do we look at if we're trying to distinguish different types of objects, well, maybe we have some map we calculate its entropy, or we have a matrix we calculate its Jordan canonical form. In all these cases, we want our calculation to be something we can actually do. Well, by this I'll mean sort of a Borel, something that at least can be computed in a Borel, if not continuous, way. Well, if we have a way of coming up with an invariant for F, and we have a reduction from E to F, it says we can really use the same sorts of invariants for E, because I just take my elements from my space where I have my equivalence relation E, I use the Borel reduction. Two things are E equivalent if and only if they're images are F equivalent, I calculate the invariance under the F equivalence relation, and think of this as saying, well, I've calculated these, composing the calculation from the F invariance with my Borel reduction is giving me some nice way of calculating some invariance for my E equivalence class. So this, at least the idea behind this is having a Borel reduction from one equivalence relation to the other says the sorts of invariance we would need, or the complexity of the equivalence relation, is no worse than that of F. So we can look at, first of all, we can look at the abstract structure of this Borel reducibility hierarchy, but we can also ask where various natural problems fall in this. I'll come to this in a second. And I think this is exactly what I just said. The other direction sort of works as well. If we show that some complicated equivalence relation is reducible to the problem we're interested in, it says that we can't necessarily find nice invariance for what we're looking for. So if we have some sort of known example of an equivalence relation where, say, we know it's not possible to find a single real number as a complete invariant, if we can reduce that to the classification problem we're interested in, it says here, too, we won't be able to find a single real number as a complete invariant. So you can show something that's complicated by taking something that you know already is complicated and find a Borel reduction to it. And we have several canonical sort of standard examples of things that we know pretty well where they relate to one another, and we use these sort of benchmarks to try to compare to other different new problems. So I just want to mention some of the different types. So the simplest equivalence relations are what we call smooth. And these are exactly the ones where you can find something like a single real number as a complete invariant. They're ones which are Borel reducible to the identity on, say, the reals. Saying we have a function that computes a single real number, two elements are equivalent if and only if they actually get computed the same real number. And being smooth, well, this statement is not true in general. It's only true it's true in particular among things where all the equivalence classes are countable. That being smooth is equivalent to saying, in a Borel way, we can pick out a representative from each of the equivalence classes. And these are really what we think of as being concretely classifiable. They're the ones where it's not too hard to tell when two things are equivalent. There are non-smooth equivalence relations. I say canonical because, in some sense, it's among Borel equivalence relations. This is minimal non-smooth equivalence relation, what we call E0. So we look at, this is just a one-directional sequences of zeros and ones. We say two of them are equivalent if they differ on only finitely many coordinates are the same beyond some point. This is really essentially the same as what's known as the Vitali equivalence relation, where we say two real numbers are equivalent if they differ by a rational. They have the same complexity in terms of the Borel reducibility hierarchy. This is known not to be smooth. Easy way of seeing this, if you know some ergodic theory, is that if you try to find a reduction to the identity, well, it has to be constant on the set of measure 1, because you can think of this as essentially being given by the, I think I have this written down, the odometer map, which essentially is adding 1 in the p-adic integers. If you think of this sort of in the other direction, it's adding 1 with carry to the right, but now you have an infinite sort of odometer. That's an ergodic map. So in particular, we know that this doesn't admit single real numbers as complete invariants. If we could reduce this to some other equivalence relation, we know that other equivalence relation also won't admit single real numbers as complete invariants. But E0 is sort of the next step up from smooth, or what we call hyperfinite, something that is written as an increasing union of a sequence of Borel equivalence relations with finite equivalence classes. In the case of E0, our finite equivalence relation, the nth equivalence relation, says the two sequences are exactly the same beyond the nth digit. It turns out being hyperfinite is equivalent to just being given by an action of the integers. There's a single invertible function. Two things are equivalent if they end up in the same orbit. That's a theorem, but it's relatively straightforward. So again, I think I mentioned this before, we say the equivalence relation is countable, not if there are countably many equivalence classes, but rather if each equivalence class is a countable set. These turn out to be exactly the things that are given by at least Borel measurable actions of countable groups. These are somehow more nicely behaved than arbitrary equivalence relations. They have a lot of nice properties. E0 in particular is countable. Actually, everything we talk about today will be countable equivalence relations, but not everything is. Turns out that there is, well, it turns out actually the structure of countable Borel equivalence relations under Borel reducibility is immensely complicated. There are lots of anti-chains, lots of incompatible things. It's a hugely complicated ordering, but there's a maximal element. There's a countable Borel equivalence relation to which every other countable Borel equivalence relation can be reduced. And there are several examples. Any two of them, really, we can reduce one to the other, so they're essentially the same in terms of complexity. Here are some examples. If you look at formal equivalence relation of Riemann surfaces, it's not literally countable, but it's bireducible with something that is a universal countable equivalence relation. If we look at the free group onto generators, F2, which we'll come back to in a minute, and we look at subgroups of this up to conjugacy, I have to explain sort of what I mean by coding these up as Borel equivalence relations on polar spaces, but we can do that, and that's an example of a universal countable equivalence relation. The nicest one, sort of from a combinatorial standpoint, that gets used the most is what we call the shift action. So we look at the space, take the free group on two generators, look at 2 to the F2. Think of this as saying we look at all the elements, it's all of the functions from our free group to the set 0, 1. Or you think of it as labeling each element in the free group by either a 0 or 1. And we define what we call the shift. We have an action F2. If you think of it as labeling the Cayley graph of F2 by 0s and 1s, and it's saying we take a group element and sort of slides that labeling along the Cayley graph and gives a new labeling. And two sequences are equivalent if one of them can be shifted to the other. Here is our main result, that if we look at one-dimensional subshifts, this is actually an example of a universal countable Borel equivalence relation. So this tells us a few things about it. It tells us in particular it's not smooth. We can't find a single real number as a complete invariant for the isomorphism. It's at least as complicated as any equivalence relation that we could induce by some action of a countable, as the orbit equivalence relation of some countable group. But it also tells us it's not, there are things much more complicated. I'll mention some examples in a second. But this is what I just said. So what are some more complicated things? I'll go through this quickly. They're just sort of telling you it can get much worse than this. You say something's classifiable by countable structures if we can assign really the isomorphism type of some algebraic structure as complete invariant. Maybe we can assign a countable graph and two objects are equivalent if and only if they get assigned isomorphic graphs, or maybe a tree or even a countable group, something like this. So these are more general than any countable Borel equivalence relation. Any countable Borel equivalence relation, there's a way to code up the equivalence class, which is a countable set, just as a structure. But these are strictly more complicated. You can think of these as actions of the infinite, things given by actions of the infinite symmetric group. Isomorphism of countable graphs is actually a maximal equivalence relation among these. It's as bad as any sort of classification of countable algebraic structures can get. And again, this is beyond what the universal countable Borel equivalence relation is. We can also look at more general Polish groups, things possibly more complicated even than the infinite symmetric group. And these all give us, well, I should be a little bit careful. They're not actually all Borel equivalence relations. Some of them, in terms of definability, there are what we call analytic sets, that are the continuous images of Borel sets, which are somewhat more general. But they're still nicely behaved sets. They still have all the usual regularity properties that we expect from the Borel set. So once we move out of countable groups, we tend to move out of the Borel setting into the analytic setting, but we can still think about this. And we can get things that are more general. There are things that are orbit equivalence relations of Polish groups that aren't classifiable by countable structures. So let me just put these all up. Here's some examples. Possible result of Ornstein is Bernoulli shifts. Those can actually be classified by the entropy. The entropy, again, can be computed in a Borel way, so that's a smooth equivalence relation. Torsion-free abelian groups of rank 1 is non-smooth, but it's hyperfinite. Sort of a group theoretic classification of this, if you look at what it says from descriptive set theory standpoint, tells you that. Linear operators up to conjugacy is more complicated than E0. It's not hyperfinite. Conjugacy of ergodic measure preserving transformations is even more complicated. It's not even classifiable by countable algebraic structures. Look at Polish metric spaces. So we actually care about the metric, the space, and look at them up to isometry. This is actually as complicated as any orbit equivalence relation can get. There's a maximal, and there are other examples of this as well, but it's saying there is a maximal element among all of the orbit equivalence relations of Polish groups, and this is an example of this. We can even actually move outside of this. There are things that are not reducible to orbit equivalence relations of Polish groups. If we look at fix some Polish space, look at all of the Borel measurable automorphisms, so bijections in space itself, so that the inverse image of Borel sets is Borel. Look at these up to conjugacy. This actually gets much worse. So countable Borel equivalence relations, the universal one is somewhat complicated. It's certainly well beyond smooth, but this just gives some idea that things actually can get incredibly more complicated even beyond that. Okay, so this tells us roughly, hopefully, some idea of what we're trying to show. We're trying to give a gauge of how complicated this problem is, classifying subshifts of isomorphism, among the sort of things that we're, at least we in the field, are familiar with, sort of standard examples, and this gives some idea of where this is going to fit among other classification problems and somehow in the general structure of this Borel reducibility hierarchy. This is sort of an intermediate point, so if you have any questions, now would be a good time. We're ready to move on to subshift. So, started the part about descriptive set theory by saying we wanted to look at a Polish space and a Borel equivalence relation on that. We want to see what does it mean to say that we have a space of subshifts, that we can represent these as elements of some Polish space. So it doesn't matter what we call our alphabet, we'll just call it the elements 0 up through n-1, can have size n. In fact, we'll really focus just on the case where n equals 2, and it'll turn out that that will be as complicated as even any larger alphabet. Somehow, in fact, you can always sort of somehow code a subshift on a larger alphabet into one of just 0, 1. So we'll define our space of closed shift invariant subsets of n to the z. Again, I'm taking n to be the set 0 up through n-1. Well, we can look at the space n to the z, what we call the hyperspace of compact sets. K of n to z is all compact subsets of the space. This turns out to be a Polish space under a topology called the torus topology can be given a metric called the Hausdorff metric. So it's a nice space, and it turns out that this is a closed subspace of k to the n z. I'll just sort of skip over this. It turns out that the set of solutions to any equation is a closed set, and we can represent that this way. And so we can view it as a closed subset of a polar space, so it's a polar space in the relative topology. And that's what we're going to mean when we talk about the space of subshifts. We have a way of representing each subshift as an element of this Polish space. And I just want to say something about the representation of forbidden words, because the thing to be careful about is two different collections of forbidden words might give the same subshift. They might rule out the same infinite sequences. But we can also view, again, I'll go through this quickly, this is just sort of another way of thinking about how can we code up subshifts as elements of a polar space. Well, we can think of a sequence of forbidden words and identify each word as a finite sequence and look at sequences of forbidden words as representing subshifts. It's not uniquely determined by this. There's at least one representation of each subshift, but there are, in general, lots of different forbidden word representations of the same subshifts. However, if we say two sets of forbidden words are similar if they give the same subshift, it turns out that, first of all, the calculation of our original representation as a closed shift invariant subset from the set of forbidden words is actually Borel measurable. And it turns out that then this idea that two sets of forbidden words being similar is actually a smooth equivalence relation. And from this standpoint, it says it really doesn't matter which of these representations we use. It still gives us a nice way of thinking about our subshifts as coded up by some elements of some Polish space. So what about the isomorphism relation? So we'll define this. We'll say two subshifts x and y are E. We'll make our equivalence relation E, just saying that they are isomorphic. And so first of all, we want to show this is a universal countable Borel equivalence relation. We should show it's a countable Borel equivalence relation. Well, the countable part is easy because of the Curtis-Hedlund-Leiden theorem said that an isomorphism was witnessed by a block code. And so there's actually you can, a little bit careful, you can set up the group of isomorphisms given by block codes, and there are only countably many block codes, so it's a countable group. So a subshift can only be isomorphic to at most countably many other subshifts. There's a calculation, don't focus on this too much, that actually tells us this is what's called sigma 0 3 set in our space, well, in our space squared. So it's sigma 0 1 is open, pi 0 2 are G delta intersection of countably many open sets. So this is a union of the intersection of countably many open sets. So it's beyond open or closed, but it's not really too bad. But it's Borel. That's what we really want to know. So I said we'd focus on the alphabet with just two symbols. Of course, one symbol doesn't give you anything. It's just one subshift. So this is sort of the minimal interesting one. And in fact, it turns out that this is complicated as it gets. So we'll just look at the alphabet 0, 1. And what we're going to look at is trying to reduce the shift action on F2, which is a universal countable Borel equivalence relation. I should say a little bit about why that's true. We said a countable Borel equivalence relation could be given by an action of some countable group. Well, if you're careful, without too much work, you could represent that as a sort of lifted up to an action of the free group on countably many generators. You can appropriately embed the free group on countably many generators into the free group on two generators. It appears as a subgroup, and if you're a little bit careful, then you can embed this all into the shift map. Very, very highly glossing that point, but it's not too bad to see that this is universal. It sort of is a very abstract, but combinatorially nice example, which is why we want to look at it. Needs slight technical clarification, which is we don't have to look at all possible labelings of the Cayley graph. We don't have to look at all possible functions from f2 to 0, 1. It'll be enough we can find a sort of a nice collection of them. The technical point here is, in general, I might have two different elements of this space that only different on one or two coordinates, but that would be enough to make them non-equivalent. I want to look at a nice set where inequivalent things actually differ in a lot of places. When I sort of try to reduce this to isomorphism of subshifts, I want to have a little bit of sort of, how to say this, just a little bit of sloppiness. I want to be able to make sure that just because things are different on one place, I want to have enough chances to sort of see that differences between two sequences are going to give me different subshifts. So that's sort of a mild technical point. Yes, sorry.
In this embedding of big free groups in F2, should I be seeing the Tarski conjecture in there somewhere, or is that right here?
I hope not.
Okay.
No, I don't. It's really the fact that if you can represent one group as a subgroup of another, and there's sort of enough space left over, you can you can take an action of the first group and represent it as an action of the second group. Yeah, I don't think the Tarski conjecture, I can't think of any.
What is
that any two non-abelian free groups have the same first order theory?
Yeah, I don't know of any way that comes up.
Okay.
I also don't personally know anyone who really understands what's happening with that. So
Same with claims too.
Anyone I don't know anyone working in this area who knows anything about that. So
Okay.
I don't know, maybe Simon Thomas, but no one ever mentions it. So I'm assuming it's not relevant. Yeah. Okay, so I'm going to proof, and I have somewhat overambitious. I have a proof here written out, but I'll go through this and maybe try to just highlight the key ideas. It's probably a little bit hard. So first of all, think of A as sort of this nice set where two things are shifts of each other, they're equivalent, but if they're not equivalent, it means that no matter how you shift them, they're always going to still differ on infinitely many coordinates. And we'll try to reduce the shift action on the sort of nice set to the isomorphism relation on subshifts. And the idea is that given an element, well, really the set A, but in fact we can do it for any element of 2 to the F2, we're going to produce a subshift. And we want two elements to be shift equivalent if and only if they produce isomorphic subshift. The idea is to somehow try to encode the orbit of an element of our shift space, sort of somehow encode the whole orbit into the shift in a way that we can, if two sequences were shifts of each other, we can somehow rearrange the shifts in the sense of F2. If two things were shifts in the sense of F2 of one another, the corresponding subshifts we can somehow rearrange in a nice way to get an isomorphism of the subshifts. So we'll denote concatenation just this way. The length of a finite sequence, standard notation. F2 again, tree group on two generators. We'll call A and B those two generators. So the idea is we have a labeling of the free group on two generators, just reduced words in A and B by zeros and ones. We want to somehow produce a collection of by infinite sequences of zeros and ones, which is shift invariant and topologically closed. So I somehow want to encode group elements into sequences. I'm going to start by just picking, it's not really important so much what these are, but they both all end with 2 1s on both sides and have some pattern in the middle. Think of these as encoding of the generators and their inverses and the identity element in the free group. And from this, by putting these together, I can think of a way of coming up with a finite sequence, which is going to represent or somehow encode each reduced word, each element of the free group on 2 generators. I'm going to somehow sort of try to fit these into my sequences that appear in my subshifts. And these all have length multiple of 8. That's somehow important later. I'm also going to want to encode individual digits. So I'll just come up with these 2 patterns. The point is, again, these are things I'll be able to recognize later when I see them appearing in some element of the subshift. They both have length 3. I'll enumerate all of the elements in my free group on 2 generators as a countable group. I'll just number them from 0 onward. And just another bit of notation. I'll use 0 bar to indicate an infinite sequence of zeros, either on the left or on the right. And I'll use S bar in general to indicate that I have S repeated over and over. So this will be a periodic point in the subshift. It'll just be a single sequence repeated in both directions infinitely often. And finally, I will let P of I denote the I prime number. So here is, this is really the heart of the argument. This is how I construct my subshift. And let me just say what's happening. So I started with, remember X is, think of it as a function from the free group to the set 0, 1. What I'm encoding here is each possible, laser pointer, I have a element, each possible element of my free group can shift X around and give another equivalent element in the equivalence relation I'm trying to reduce. So I'm going to look at each possible way of shifting my original point X and recording particular digits of X. Again, X is a function from the free group to 0, 1. And I'm going to remember this, I'm going to include some long string of zeros in the middle here, which is somehow going to let me recover K. In other words, help me recover which particular digit of X I was looking at. And then I'm also throwing in some periodic points. The point about all of these are the periods will be various distinct primes. I'll be able to find those. So I take all of these sequences and all of their shifts, and I take the closure, that gives me something that's topologically closed, and shift invariant. And this is going to be the subshift that I have for X. And again, the idea here is, I'm going to go through, really not say too much about the details, but the idea is that I've somehow encoded the whole orbit of X, an element of 2 to the F2, somehow encoded the whole orbit into the subshift in a way that I can recover by looking for these periodic points, and then I can somehow read off what, I can't find X itself necessarily from the subshift, but I can at least recover the orbit of X. And this will say that 2 things have the same orbit if and only if they produce the same subshift. So 2 things are equivalent if and only if the subshifts they get are isomorphic. And I really don't, I have this written down, but I'm just going to go through and, I guess, let me just jump sort of
There's not going to be a quiz at the end, right?
There's not going to be a quiz at the end. If you're interested in this, there is actually a paper, so you can actually read this. Just sort of look at these last 2 lines. If I had X and Y that differed just by the generator A, and these A, Y, and AX were sort of the sets that were generating the subshift. We're taking the shift closure of them. The point is that we sort of, the only thing that's differing is that here we are looking at our encoding. Remember what row was? It was taking a word in the free group and turning it into this length, the sequence of some length multiple of 8. It's saying the only difference here is at the end, and then everything else is followed by zeros. Rather than encoding some word, here we're encoding that word followed by a index. The point is we can look for this. We can find these patterns. We can find that we have a long string of zeros at the end, and just essentially strip off or add an encoding of A to get an isomorphism. So this is sort of some abstract description of what the block code should look like. It's essentially saying we're going to try to put in add an A inverse to our reduced word at the end, and we get an isomorphism.
And your rows and your Ds were constructed so that they had ones at the ends of them, right?
Right.
Okay.
That was the key point, is we can find those by looking for the ones. And they're distinct enough from one another. We have to look, I think you need a block code of, I can't remember, I have this written down, I think so, yeah, 16 I think was the far enough of a window, and if you look 16 places away in each direction, you could see where you were in the sequence. I guess going through very quickly. The other direction, we want to see that if the subshifts are isomorphic, they actually came from sequences that were shifts of one another. This is where we needed that little bit of sloppiness. The point is that the way we set this up, we can find an isomorphism between subshifts has to preserve periods of points. So it has to somehow map points of the various periods that we pick to have different primes to one another. That introduces a certain sort of rigidity in what the isomorphism looks like. It really allows us to recover everything else. I probably should not try to force too many of these details on you. But the way this is set up, think of it as the periodic points limit what sort of isomorphisms we can have between the subshifts we produce this way. And once we look at those, we can pull off the structure of the orbit the way it was encoded by these strings of length 8 or what have you, and recover not x necessarily, but the orbit of x. And that's really all we needed. But let me skip through this. Okay, so allegedly I told you how to prove this. At least maybe some idea of this. So this tells us this is a universal countable Borel equivalence relation. We can go a little bit beyond this if we look for what we call n-dimensional subshifts. Well, it actually is going to actually have the same complexity. These are all universal countable Borel equivalence relations because they're all countable again. They're at least it's fairly straightforward to see they're at least as complicated as one-dimensional case. This also says they have all the same complexity, which is a little bit surprising, maybe, because there are certain ways in which two-dimensional subshifts have a richer structure than others. For instance, in the case of finite type, if you look at two-dimensional subshifts of finite types, you can get different entropies than you can get them on just one-dimensional subshifts of finite type. But this says, at least from the Borel standpoint, Borel reducibility standpoint, they're really the same. In fact, let's say a few more things very quickly. The proof that I gave here, or claim to have given here, really used periodic points in a fundamental way, but this is actually not necessary. You can get rid of this fact. So we say a subshift is free if it contains no periodic points. And in fact, you can show, it's a significantly more complicated technique, but you can show that if you just look at free subshifts and look at the isomorphism problem here, it's the same complexity. It doesn't get any simpler if you restrict yourself to free subshifts. You can also look at other groups. think of a subshift as an action of the group Z, a two-dimensional subshift of the group Z squared. But we can look, well, the shift I talked about originally of the free group on two generators, that's the full shift of F2 on the space. We can take any countable group and we refer to these as G subflows. They're invariant under the group action and topologically closed subsets of 2 to the G. And we can look at define isomorphism and freeness in the analogous way. Some groups actually turn out to be really too simple. A group is locally finite if whenever you take a finite subset, it generates a finite subgroup. Well, these turn out actually not to be very complicated to classify the subshifts or the subflows up to isomorphism. They actually are just the complexity of E0. So they're dramatically simpler than for the integers. However, this is really the only impediment. If we have a countable group that's not locally finite, we look at the free G subflows. The isomorphism of these is the same universal countable Borel equivalence relation. So I just want to mention one sort of glaringly open problem about this. So sort of really the building blocks when you look at dynamical systems are the minimal ones. They're ones that really can't be decomposed any further. Every point, the orbit of every point is dense, so if you try to find a closed invariant subset, you can't get any smaller. There's a nice classification for subflows, essentially saying they're almost periodic. You think of a subshift on Z, it says anytime you see a particular pattern, if I look anywhere else along the sequence, there's some fixed distance I have to move in one direction or the other to find that pattern again. Well, an example of this is the two-more sequence. Seen this, trying to figure out the pattern there. But we don't know how complicated. We saw that if we just restrict to free subflows or free subshifts, it doesn't change the complexity. But we don't know about minimal. Maybe it's much easier to classify minimal subshifts up to isomorphism. We don't have really any good idea. The only thing we know is that E0 is a lower bound for the free, well, really the free are interesting. Non-free minimal ones are just really finite things. So these are really the ones we're interested in. They know that E0 is a lower bound for any group, but this is all we know. Of course, we know universal countable is an upper bound because all subshifts, all subflows have that complexity. So, but in particular, this says for the locally finite groups, we know the exact answer, that E0 is an upper bound and a lower bound, but in general, we don't know minimal. So this seems a very hard problem. And oh, only 10 minutes over.
Other questions?
Yeah, John, you mentioned a topology. Was it the torus?
The torus.
Yeah, the torus. Is that easy to describe?
Yeah, it's easy to describe. There's about a 50% chance I will do it incorrectly. But we take, so what are we looking at? We're looking at the compact subsets of X. So what is, we can give a basis by, if we look at U subset of X open, if we look at the set of K such that K is a subset of U as one set, or also the set of K such that K has non-empty intersection with U. So these are subsets of K of X in both cases. These give me, as I let U range over all the open sets of U, this gives me a basis. Much easier to understand it with the Hausdorff topology, where I say well, if I look at two compact sets, I can measure the distance between them, because if I take any point in one set, I can find, because of compactness, I can find a minimal distance to the other set. And I just maximize among this. So I take the supremum for x in K1, the infimum of y in K2. The regular distance, I put some metric on my space x, the distance between x and y. So here's x, I find the minimal y, and now I pick sort of the largest, the worst case scenario of this, and then I symmetrize this primum of x in K2, primum y in K1. And this actually gives me a metric. I find it easier to understand it this way.
Just maybe out of curiosity, any of this could be applied to, for instance, Lorentz attractor things Mike's is doing, for instance.
How are the symbolic dynamics of lens attractors? I don't really know.
Yeah, well, there's one branch who's looking at shifts of finite type, and actually we have some questions I'll talk to you about later. Where we so shifts of finite type, okay, there's the Waves conjecture which is false. Then if you take what are called flow equivalents, that means they can be cross sections of a flow, the same flow. So you can be different shifts, but you can be across the same flow. That equivalence relation is easy. There's a computable invariant for it. And John Strange worked that out. Then, however, if you add additional information about the flow as you're moving along, say how things are twisting or something, you get basically a skew product with a finite group, say 0, 1. So it's like labeling the graph with elements of some group. So you have something like that. Then we don't know how to classify it. And we don't know if it's decidable or not. We don't know. So I was going to show you that later.
Yeah,
it's going to take a while to show
this
you.
doesn't say too much if you just restrict to finite type, because there are only countably many of these. And this is somehow saying to really get a complicated equivalence relation in the sense of Borel reducibility, you need an uncountable collection, because from a Borel standpoint, if you have countably many things, I can number them.
Yeah.
Although there are some finer things like
computability. Yeah, computability becomes an issue there, but just sort of this broad Borel reducibility doesn't say too much of that.
Okay.
All right. Thank you very much.